Okay, so we've got this function given, and the very first thing I want to notice about this is it's a product of a polynomial and a sine function. Wait a second, it's a sine function of a polynomial. Sine is continuous, polynomials are continuous, products of continuous functions are continuous. Then over here I have another, I have a polynomial z, that's continuous. Exponential, everything in sight's continuous, right? And so this function is, I kept saying continuous. What I meant was differentiable. Let's see here. So let's compute some partial derivatives, and the same thing's going to happen. So here we go. Partial of f with respect to x. Now let's see here. Well, product rule problem. Right? So 2x sine x minus 2y plus x squared cosine x minus 2y times the derivative of x with respect to s times 1, and then minus yz e to the xy. So that's the x partial, and then likewise for the y partial, and likewise for the z partial. I'm going to let you do the algebra. That's just a bunch of algebra. Is that cool? Okay. There's a bunch of details there, but yeah. Okay, and what you notice about this is that all these partial derivatives are also continuous. They are sums of products of compositions of all known continuous functions. So because the partial derivatives are all continuous, that means these are continuous, and that means that f is continuously differentiable, and that means that f is differentiable. And that's what we are going to make big use of here. Everybody good? Cool? Okay. Okay, so the question says compute these directional derivatives. And in this case we have, so the question you've asked me about, number 4 here, we've got an a and a v given. Well, since the function's differentiable, I can compute the directional derivatives. By multiplying the Jacobian matrix times the velocity vector. Well, this function, the Jacobian matrix, let's see, there's only a single output value, so the Jacobian matrix is just a single row matrix. The Jacobian is partial of f with respect to x, partial of f with respect to y, partial of f with respect to z, and then I'm going to multiply that by the given vector, in this case negative 3, 3, 8. And now, of course, these partial derivatives, there's a bunch of stuff in here. These, all that junk up here that we just did the first one, and I'm going to let you do the rest. And you got to plug in the point, and so there's a certain amount of tedium in taking that, plugging it into there, and then putting that into there. But it's just kind of tedium. Yeah, is that cool? You can do that?
Yeah, that's what I did. I just needed to make sure.
Oh yeah. Okay, yeah, cool. So here's the neat thing about doing it this way. By the way, a different thing you could have done on this problem is you could take, and I don't encourage this, but you could take the a and the v and write down a plus tv and compute the directional derivative the old-fashioned way, right? It'd be a lot more work. Right? But even more so, once you've gone to all the trouble to compute, this Jacobian matrix. Once you know that Jacobian matrix, notice the Jacobian matrix at that point is the exact same as the Jacobian matrix at that point. So if you do it this way for number 4, number 5 becomes really easy. Same matrix multiplied by this different vector, it's 2 lines. So yeah. Okay, is everybody good? I'll also quickly observe that a similar convenience happens with these first three parts because they're all at the same point. And so you compute the Jacobian matrix once, and then that one matrix gets multiplied by these three different vectors. So boom, boom, boom. Yeah. Okay.
Yeah, I have a question. Like, this Jacobian matrix means that you just make the partial derivatives as the column of the matrix. Is that what?
Yeah.
Is essentially?
Yeah, that's right. That's the formula for the Jacobian matrix. Again, there's a little asterisk there that is you can call it the Jacobian matrix, and it behaves nicely and computes derivative transformations only if the function's differentiable.
Okay.
But yeah, totally. Okay.